This is a review of derivatives as used in dynamics, and this is the most general form. The derivative with respect to x of u to the n is equal to n u to the n minus 1 du dx. Here u is a function of x of some sort. It could be a simple function of x, or it could be more complex like a polynomial, but you would use this general form if trying to find the first derivative with respect to x. The first general form of the product rule is if you have a product of two functions of x, is u times the derivative of v with respect to x plus v times the derivative of u. In dynamics, we often need to take the time derivative of a function of x or a function of y or something like that. And here we need to use the same kind of form, d to dx of u to the n, which is this stuff up here, times dx dt. If we're looking for if u is a function of x. This allows us to put the terms into a function of time now. Same thing with the product rule. We have u times the derivative of v plus v times the derivative of u. And here we'll use the v dot and u dot, designating that these are time derivatives, dv dt and du dt. Okay, so here's some simple examples of chain rule. Where if you want to take the time derivative of 3x, that would be 3x dot. If you have a raised to the exponent, raised to the exponent 3, so it'd be d dx, it'd be 9x squared is your d dx, and then we have a dx dt, that's the x dot. Here we have u raised to the n power, so I'm going to say that that is 2 times 3x squared plus 3 raised to the 1 power. Now I need du dx, which is the derivative of this part, is 6x, times dx dt. Alright, and then the product rule examples, again fairly easy, but what we'll have is that I've put u and v with little lines under here, so I'm going to say that I'm going to take the time derivative of 3x x dot, so that's going to be the derivative u, which is 3x times the derivative of v, x double dot, plus v, x dot, times the derivative of u. The derivative of u is going to be 3, that's going to be the du dx, and the x dot is the dx dt. And then when we simplify it, we get an x dot squared. And this is really typical kind of derivative look, that you'd have an x double dot and an x dot squared in your answer when you get done. If you have something like this, 3x cubed times x dot, I'm going to take the 3 out, factor that out, and now I'm just going to do the u and the v on the inside. So take out factor out the 3. We got u times the derivative of v is x double dot, plus v, which is that, times the derivative of u is 3x squared. You're going to take that 3x and make it 3x squared, or take that x cubed, make it 3x squared. Then I still need my dx dt on the end. And again, if you take a polynomial raised to a exponent, you could say that that is, this term is my u, this is my v, and when I get done, I'm going to take u times the derivative of v, so I'm going to take that whole term times v double dot plus v times the derivative of u, and here I'll have to do the regular derivative concept here, where I'm going to put the 2 times 3x plus 3 raised to the 1 power. Now I have to do du dx, so or dv, let's see, is that my, yeah, du dx would be the 3, which is the derivative of that, and I still need an x dot on the end. Alright, if you had a couple of expressions that looked like this, just want to show you how they might look related. Here we have let me go back. These are expressions. That's what I wanted to say. These are expressions. These are not equations. We're taking chain rule and product rule examples of an expression, but most often in dynamics we have equations that we need to take derivatives of. And here you may have y equals something, and that would be an equation, and we have to, whenever we take the derivatives, the time derivatives, we'd have to do the same thing to both sides. So again, here's several expressions, 3 of them, and what I'm going to do is take the derivatives going vertically here. So I'm going to say, first I'm just going to take dy dx, and in calculus often you use y prime as dy dx, and I want to distinguish y prime from y dot. Very important distinction. Because usually the prime means the derivative with respect to x, whereas y dot means the derivative with respect to time. Okay. So let's just take, this would be the derivative of y would be 2x, derivative of y x squared plus 2. Since that's a constant, it's still just 2x. Take the derivative of this time, y prime, it is 2x, this is a u to the n, so it'd be n u to the n minus 1 raised to the 1 power, and then du dx would be the 2x. Putting the chain rule for time is essentially just taking dy dx, which we just did here, and then multiplying by dx dt, which is x dot. And so that's what I've done to those expressions, and you can see how I did that. To take the second derivative, which is y double dot, again, we're going to take the derivative with respect to this side, which is, if that side is y dot, we're going to take the derivative again, it's just going to be y double dot. Here I have to use the product rule. I'm going to call that my u, that my v. So I'm going to say that that is u times the derivative of v plus v times the derivative of u, which is that, times x dot. And again, because the 2x is not a function of time, when I want to take the time derivative of it, I take du dx, dx dt. That's what those two terms are. Factoring it out, and it looks like that. Same thing over here. This is much longer term since I have a two-term polynomial, but I can take the time derivative of that, or of this expression, y double dot. Again, I'm going to say that that is a u, that is a v, that is a u, and that's a v. So I got u, 4x cubed, plus v, or times v is x double dot, plus x dot. Oh, I'm sorry, here, this x dot times the derivative of u, which is 12x squared, times another x dot. I do the same thing with that term, and you can see what that looks like. So this is all one long expression. I just put it on two lines. Here's another example. This is in your notes, that if you have a cubed equation, you might just want to find y dot and y double dot, and using that kind of approach. Okay, how about here I have one equation that can be expressed in two ways. The equation is y squared equals 4x, and again a line can be expressed in that way, but let's take the time derivative of it expressed like that and compare it to the time derivative of it if expressed like that. So again, these equations are equivalent. I just took the square root of both sides here, and I get that. And so follow me down, because this is now an equation. Whatever I do to one side, I have to do to the other side. So if I take the time derivative of this, I get 2y, y dot. Over here, I get 4x dot. And over here, let's put this way, the derivative of time is y dot. And here I got 2, I'll factor that out, and I get the 1/2. And then x to the n minus 1, which would be minus 1/2 times x dot. Simplified, it looks like that. So are those two the same? Well, we're gonna find that out down below. Let's take the second time, do the second derivative. Here we will have to use the product rule, and I'm going to take the derivative, time derivative of this. So I'm going to say that that is my u, that is my v. So I got u times the derivative of v plus v times the derivative of u. Now on this side, I just get 4x double dot. Over here, I will say that that is my u and that is my v. So that is my u times v dot plus v times u dot, and that's what I get there. All right, so when I get these two expressions, are they the same? That's the question. Well, let's do some substituting and figure that out. So over here, I took this equation for y, or this, sorry, it's off the page. I took this equation and I set it equal to y dot, which is right here. And I get this expression. Then when I have this 2y in the denominator, I took the expression for y from over here and plugged it into there. And trying to figure out if the derivatives are the same, I simplify this and I get the y dot is equal to x to the minus 1/2 times x dot, which indeed is the same thing as I have on that side of the equation. How about the second derivative, the y double dot? Here I took this equation, set this equal to y double dot, and that's what I get here. And then I simplified that a little bit, and I put in for y dot, I believe that's my y dot, I put y dot in from this expression, put that here, and then over y I put this expression back in there. And again, simplifying it, you can follow my math, but it does agree that that taking the derivative this way still gets the same answer as you did over there, which is nice to know. So it doesn't really matter. You don't have to put it in terms of just y. You can take your derivatives in terms of y squared if you're careful, and it works fine. All right, here's just a couple more things. Here are some chain rule, product rule examples with sines and cosines. And remember that if you have r as a function of theta, to take to find r dot, you have to do dr d theta dt. And so I did that with this expression. 3 is that the derivative of sine is the cosine, but then I need my theta dot, and so this would be the expression for r dot. To take r double dot, I divided it up into calling this my u and my v, so I can use the product rule. Factored the 3 out, so this is u times the derivative of v plus v times the derivative of u, and now that's my dr d theta, and now I need my d theta dt underneath the inside, using the chain rule inside the product rule. All right, then the last thing is here's an expression for 5 cosine squared theta plus 2. And just you do the same thing. This is kind of a little longer and involved, but the thing to remember here is that cosine squared theta is actually cosine theta squared. So this is a form of u to the n. So when you take the derivative of that, it is n u to the n minus 1, and that's where we get some of these terms under here. But anyway, so cosine squared theta is the same as cosine theta, the quantity squared. Well, anyway, I hope that helps understanding derivatives.